All right, welcome back to The Explainer. Today, we are diving into a really cool problem. It's one of those that gets slapped with a hard label on LeetCode, and trust me on this, once you grasp the core idea, it's actually super elegant. We're going to crack the closest binary search tree values problem.
So before we even touch the code or get lost in the weeds with trees and nodes, let's just think about the big picture. Imagine you're in a massive library, right? And all the books are perfectly sorted by publication year. Your mission, should you choose to accept it, is to find the 2 books published closest to, let's say, 1984. Now, how would you do that efficiently? Without having to look at every single book. That puzzle, that's pretty much exactly what we're solving today.
Okay, so here's our game plan for breaking this down. We'll start by figuring out what the challenge actually is. Then we'll uncover the secret sauce of the binary search tree. After that, we'll get into the sliding window strategy, see it work with a real example, connect that logic to the code, and then we'll talk about making it even faster. Let's get to it. All right, first up, the K closest values challenge. Before you can solve anything, you've got to know exactly what the goal is. So let's define the problem.
So here's the deal officially. The problem hands us 3 things. First, a binary search tree, or a BST. Don't worry, it's just a smart way to organize numbers. Second, we get a target number, could be anything, even a decimal. And third, we get an integer, k. Our mission? Find the k numbers in that tree that are the absolute closest to our target. Simple as that.
Okay, let's make this real with an example. So our tree has the numbers 1, 2, 3, 4, and 5. Our target is this funky decimal, 3.714286. And k is 2, which means we need to find the 2 closest values. So if you look at the numbers, which 2 are nearest to 3.7? Well, it's got to be 4, which is super close, and 3. And yep, that's exactly what the output should be, 4 and 3.
Okay, on to our next piece of the puzzle. And folks, this is the aha moment. This is the key that unlocks the entire thing. The secret to solving this efficiently is all thanks to a hidden superpower that every binary search tree has, a built-in secret order.
And how do we uncover this secret order? With something called an in-order traversal. It sounds complicated, but it's really not. It's a super simple pattern. You just go all the way left, visit the node you're on, and then go all the way right. That's the whole mantra. Left, root, right. That's it.
And what happens when you follow that simple left, root, right rule? The result is kind of magical. You get every single value from the tree, but laid out in a perfectly sorted list. This is the game changer, right here. We've just taken this complex, branching tree structure and flattened it into a nice, neat, sorted list. And that we can work with.
Okay, so we have our sorted list. Now what? How do we actually find the k closest values? Well, that brings us to our main strategy, the sliding window. I want you to think of it like a little leaderboard. It only has, say, k spots on it. This is so much smarter than just checking every single number against our target. Instead of doing all that work, we're just going to keep a running tally of the top k contenders as we go.
So here's how this little algorithm works. First, we set up an empty list. This is going to be our window. Then, we start walking through our sorted numbers one by one. For the first k numbers, it's easy. We just add them to the window until it's full. But once it's full, that's when the magic happens. For every new number we see, we look at our window and ask, who's the worst candidate in here? The one that's farthest from our target. If our new number is a better match, if it's closer, we just kick the worst one out and slide the new one in. See? A sliding window.
All right, that's the theory. But theory is one thing, right? Let's actually see this thing in action. It'll make so much more sense when we walk through it. We'll use the exact same example from the beginning to keep it simple. Okay, here's the setup again. Remember that in-order traversal? It gave us our sorted list, 1, 2, 3, 4, 5. The target is still that 3.714, and we need the 2 closest values. So our window, our leaderboard, it's got a size of 2.
Let's start our journey through the list. First up is the number 1. Our window is empty, so boom, 1 goes in. Simple. The window now has just 1. Next, we see the number 2. We still have space since k is 2, so in it goes. Our window is now full with 1, 2.
Okay, now it gets interesting. We've reached the number 3. Our window is full, right? It's got 1 and 2, so now we have to ask that key question, is 3 a better contender than the worst one we've got?
So between 1 and 2, which one is further away from our target of 3.7? It's definitely 1. So the real question is 3 closer to 3.7 than 1 is? Well, the distance for 3 is about 0.7, and the distance for 1 is about 2.7. So yes, it's a way better match. So we say goodbye to 1 and hello to 3. Our new window is 2, 3.
All right, next up, the number 4. Our window is 2, 3. It's full, so we do it again. Who's the weakest link now? Between 2 and 3, which is further from 3.7? That's going to be 2. So, is our new number 4 a better fit than 2? The distance for 4 is just 0.3, while the distance for 2 is 1.7. Oh yeah, it's much better. So, out with the 2, in with the 4. Our window slides again to 3, 4.
And we've got one last number to check, 5. Our window currently holds 3, 4. Now who's the worst candidate here? Well, 3 is a little bit farther from 3.7 than 4 is. So the question is 5 closer to our target than 3 is? The distance for 5 is about 1.3. The distance for 3 is only 0.7. So, nope, 5 is not a better candidate. We don't make a change. And since that's the end of our list, we're done. Our final window, 3, 4, is the answer.
See, it's a pretty clean process once you walk through it. So now, let's connect the dots. How does this logic we just walked through actually translate into code? You'll be surprised how straightforward it is.
This is what I love about this solution. It's almost a perfect one-to-one translation from our plain English logic to the code. That question we kept asking, is the window full? That's just if len of q is less than k. And the comparison part, is this new number a better match than the worst one? Well, that's this line right here, just comparing the absolute differences. And kicking the old one out and adding the new one, that's just a pop and an addib. It's incredibly clean.
And that brings us to our final thought for today, the quest for optimization. Look, the solution we just went through is awesome. It's elegant, it works, it gets the right answer. But you know how it is in programming? There's always that little voice in the back of your head asking, can we do it even faster?
So if you remember just one thing from all of this, let it be this. The real genius here is how the solution leverages a fundamental property of the data structure. It takes that hidden order we get from the in-order traversal and uses that perfectly sorted list to fuel a really simple, really efficient algorithm, the sliding window. It's about using the tool's own strengths.
And this last question. This is what separates good programmers from great ones. It's that constant push for what's next. Our solution works in what's called O of n time, meaning we have to visit every single node, n being the number of nodes. But this follow-up is asking, what if we have a little extra information? What if we know the tree is balanced? Is there some clever shortcut we can take? Could we possibly find the answer without having to look at everything? Now that is a fun problem to think about. Thanks so much.